This is where curiosity turns into capability. In this section, you'll dive hands-on into Azure Machine Learning, experimenting with data, models, workflows, to see how ideas quickly translate into working solutions. It's your opportunity to explore, iterate, and build confidence by learning through experimentation, laying the groundwork for creating, refining, and scaling real-world machine learning solutions. Here we see a reinforcement of the critical idea from Section 1. Training a model is an iterative journey, not a one-time event. Here we focus on two core training paths that enable fast learning and deeper experimentation. First, automated machine learning, or AutoML, provides a powerful way to quickly explore algorithms, features, and hyperparameters with minimal setup, making it ideal for establishing a strong baseline and accelerating early insights. From there, teams can continue experimentation by running notebooks, where they gain full control over data preparation, model logic, and custom tuning. This combination empowers data scientists to move fluidly between speed and precision, experimenting, learning, and refining the model with each iteration, while performance comparison and the responsible AI dashboard are essential next steps. Those insights are intentionally covered in the following section to keep the focus here on exploration and experimentation. Consider building a diabetes risk prediction model. The team starts with AutoML to quickly test multiple classification algorithms against historical patient data and identify top performers. Once a promising model emerges, they shift to notebooks to fine-tune features like BMI, glucose levels, and age, experimenting with pre-processing techniques and model parameters to boost accuracy. This workflow allows the team to answer key questions early. Which approach performs best? Where can we optimize? Before moving on to compare performance metrics and evaluate fairness, explainability, and bias in the responsible AI dashboard. The result is a structured, repeatable training process that balances speed, flexibility, and trust, exactly what real-world ML solutions demand. Automated machine learning removes the guesswork and the grind for model experimentation by automatically testing multiple pre-processing techniques and algorithms to find the best performing model for your data. Instead of manually configuring and evaluating options like logistic regression, decision trees, or support vector machines, AutoML runs these experiments in parallel and selects the optimal model based on the metric that matters most to your scenario. It's a powerful way to accelerate experimentation while still producing high-quality, data-driven results in machine learning. For example, imagine predicting customer churn for a subscription service. You can point AutoML to your dataset, define churn as the target, and let it explore different feature transformations and algorithms to surface the best model without writing extensive training code. AutoML isn't limited to classification either. It can be used for regression, forecasting, image classification, and natural language processing, making it a versatile tool for quickly moving from data to insight while freeing you up to focus on problem design and business impact rather than manual tuning. Choosing the right task type is the moment where machine learning design truly clicks because it directly determines your training data, feature engineering approach, algorithms, and success metrics. Here we have the most common ML tasks you'll encounter: classification for predicting categories, regression for predicting numerical values, time series forecasting for predicting future values over time, computer vision for analyzing images, and natural language processing for understanding and classifying text. Each task answers a different kind of business question, and selecting the correct one ensures you're solving the right problem with the right tools, avoiding wasted effort and misleading results from the start. A practical use case is a healthcare team building a diabetes screening solution. Since the outcome is clear, yes or no, the decision whether a patient should be screened further, the team chooses a classification task, shaping their data preparation, algorithm selection, and evaluation metrics around that goal. If instead they wanted to predict the patient's future glucose level, regression or time series forecasting would be the most appropriate. This example highlights why choosing the task is foundational. It aligns the technical approach with real-world intent, ensuring the model delivers insights that are both actionable and trustworthy. Now it's time for the knowledge check. Question 1. Your marketing team wants to predict whether a customer will churn or not. Which task should you use in automated machine learning? Answer: classification. Question 2. A medical company wants to create an application that can detect abnormalities in X-ray images. Which task would be used in AML? Answer: computer vision. Before you can let AutoML work its magic, there is one thing you must get right. Your data needs to be prepared and described in a way that Azure Machine Learning can understand. For a classification model, you typically only need to provide the training data, but AutoML still needs help reading it correctly, which is where an ML table data asset comes in. ML table captures the schema and the structure of your tabular data and how to load it, so your AutoML job can consistently apply preprocessing and feature engineering. Once the ML table is created, you simply reference it as the input, like the Python snippet shown, so AutoML knows exactly where the data is and how to interpret it. Now imagine you're building a churn prediction classifier for a subscription business. Your customers' records live in a folder of files, and you want AutoML to quickly test the best transformations and models. But first, you package that folder as an ML table so Azure ML understands the columns, the types, and the layout. Then, with one clean input reference, you can run AutoML confidently, knowing your experiment is reproducible and ready to scale from a quick test to a production pipeline. Scaling and normalization are quiet heroes of successful machine learning, and this slide highlights why they matter so much. AutoML automatically applies scaling and normalization to numeric data so that large value features don't overpower smaller ones during training, creating a fair playing field for the model to learn meaningful patterns. But it doesn't stop there. AutoML also layers in optional featurization, handling real-world data challenges such as inputting missing values, encoding categorical data into numeric indicators, dropping high cardinality fields like record IDs that add noise, and engineering smarter features from raw input like date-time fields. The results is cleaner, more balanced data that allows algorithms to focus on signal instead of distortion, dramatically improving both performance and reliability. A practical use case is training a diabetes prediction model using patient health data. Features like glucose levels and insulin values may exist on very different scales, so AutoML automatically normalizes them to prevent one measurement from skewing results. Missing BMI values are intelligently inputted, categories like patient gender are encoded, and irrelevant identifiers are removed. With minimal manual setup, the data becomes model-ready, allowing data scientists to focus on outcomes. Running an automated machine learning experiment is where speed meets scale in your model training workflow. With just a few configuration choices and the Python SDK, you can submit an AutoML job that automatically selects from a rich set of algorithms based on the task you define. From classification, AutoML intelligently evaluates options like logistic regression, decision trees, random forest, gradient boosting, SVMs, XGBoost, and more, training and comparing them in parallel to determine which model performs best against your chosen metric. This lets you focus on the problem and the data rather than manually testing and tuning each algorithm. Now imagine building a fraud detection model for online transactions. Instead of guessing which algorithm might work best, you submit a classification AutoML job that tests multiple approaches at once and surfaces the top performing model automatically. With minimal code and maximum efficiency, you get a strong baseline model fast, while still having full transparency into which algorithms were tried and why one won. Restricting algorithm selection gives you the best of both worlds, the speed of AutoML and the control your scenario or organization may require. By default, AutoML explores a broad range of algorithms for the task, but here we see how you can intentionally block certain options when they're not a good fit. This can be driven by practical considerations, such as data sets that don't work well with a specific algorithm family, or by compliance and governance policies that limit which machine learning techniques are allowed in your environment. The result is a more focused, efficient experiment that still benefits from automation without violating technical or organizational constraints. Imagine a regulated financial institution building a credit risk classification model. Company policy may prohibit the use of complex black box algorithms for explainability reasons, so the team restricts AutoML to simpler, more interpretable models like logistic regression and decision trees. AutoML then evaluates only those allowed algorithms, saving time and ensuring policy compliance while still identifying the best performing model within the approved boundaries. Configuring an AutoML experiment is where experimentation becomes intentional and controlled. And in this slide, we see exactly how to guide AutoML toward the right outcome. Using the Python SDK version 2 and the AutoML class, you start by defining the task type. For classification scenarios, this means using AutoML.classification and then selecting a primary metric that reflects what success actually looks like, such as accuracy, precision, recall, or AUC. Azure Machine Learning evaluates multiple models against this primary metric to determine the best one. And you can even programmatically retrieve available metrics using the classification primary metric function. From there, you set limits to balance speed, cost, and thoroughness, controlling overall runtime, per trial duration, the number of models trained, and whether early termination should stop runs that aren't improving. To accelerate experimentation, AutoML can execute trials in parallel across compute clusters, while training properties let you fine-tune the process by excluding unsuitable algorithms or enabling ensemble models for improved performance. Consider training a patient risk classification model to determine whether someone should be screened for diabetes. The team sets recall as the primary metric to minimize missed high-risk patients. It limits the experiment to a fixed time window to control cost, and it enables early termination to avoid wasting compute or underperforming models. Knowing tree-based models work well for the structured data, they exclude less relevant algorithms and allow ensembles to boost accuracy. In just a few controlled iterations, the team identifies a strong candidate model ready to be compared further using performance metrics and responsible AI insights in the next step of the workflow. Now let's see how you can bring a AutoML classification experiment to life by explicitly configuring what success looks like using the Azure Machine Learning Python software development kit with a few clear parameters: compute target, experiment name, training date, target column, and primary metric. You define how AutoML will train, evaluate, and compare models on your behalf. Options like cross-validation add robustness to your results, while enabling model explainability ensures you can understand why a model would make certain predictions, which is critical for trust, compliance, and iteration. This configuration step turns AutoML from a black box into a controlled, repeatable experiment aligned to your business goals. Imagine you're building a diabetes risk classifier for a healthcare analytics team. You point AutoML at your prepared trained data. You set accuracy as the primary metric. You define the diabetic column as the prediction column and enable explainability to understand which features most influence outcomes. AutoML then runs multiple models behind the scenes, cross-validates them, and surfaces the best option, giving you a production-ready model faster with built-in insights to support clinical and business decision-making. Setting limits is how you turn AutoML from trying everything into a smart, cost-aware experimentation. Now we see the key controls that help you balance speed, budget, and model quality. You can define a timeout to cap how long the entire experiment runs, a trial timeout to prevent individual modules from monopolizing compute, and a maximum number of trials to limit how many models are trained. Perhaps most powerful is early termination, which automatically stops the experiment when performance stops improving, saving both time and money. Together, these limits ensure AutoML explores enough combinations to find a strong model without drifting into wasted effort or runaway compute cost. Consider training a classification model to identify high-risk diabetes patients. The team sets a 60-minute experimentation window, which limits the trial to 20 minutes, and it caps the run at 5 models and enables early termination so poor-performing models are cut quickly. Within an hour, you can get a high-quality candidate model without overspending or over-experimenting, demonstrating how thoughtful limit setting keeps machine learning projects efficient, predictable, and production-ready. Submitting an AutoML experiment is the moment where all your planning turns into action. With a single line of Python code, you launch a fully automated experiment that orchestrates feature engineering, algorithm selection, and model training on your behalf. Behind the scenes, AutoML breaks the work into child jobs, one dedicated to featurization and multiple others training different models in parallel, allowing you to explore a wide solution space efficiently and transparently. This structure gives you both speed and visibility so you can see exactly how each model was trained while still benefiting from automation at scale. Consider a data scientist submitting an AutoML classification job to predict whether a patient is at high risk for diabetes. With one command, Azure Machine Learning spins up several child jobs, trains multiple models, and returns the best performer, turning hours of manual setup into a streamlined, production-ready workflow. Once an AutoML experiment completes, this is where insight turns into informed decision-making. In Azure Machine Learning Studio, you can open the AutoML run to review a clear summary of the best model inspect the input data, and understand how each model performed against your chosen metric. By switching to the Models tab, you can compare every trained model side by side, seeing accuracy scores, explanations, and configurations, so you're not just picking the top score, but the right model for your use case and constraints. After running AutoML for a churn prediction scenario, you review several high-performing models and discover two with similar accuracy, but one offers better explainability. That visibility helps you confidently choose a model that balances performance and trust, setting you up for a smoother deployment and stakeholder buy-in. Here we see how to make AutoML's behind the scenes work visible and trustworthy by exploring the pre-processing steps it applies when you enable featurization. AutoML automatically adds data guardrails for classification, class balancing detection, missing feature values imputation, and high cardinality feature detection, so the training pipeline is resilient even when the data isn't perfect, because real data rarely is. Each guardrail reports a clear status so you know what happened. Passed, no issues found. Done, AutoML applied a fix. Review what changed, or alerted an issue was found but couldn't be fixed automatically. So you should investigate the data. And right alongside those guardrails, AutoML also applies scaling and normalization techniques for each model it trains. So you're not just getting a model, you're actually getting a documented pre-processing recipe you can inspect and explain. Here's the practical how to spot it apart. You can review what AutoML applied directly in the list of models under algorithm name, where pre-processing and algorithm often appear together. For example, MaxAbs Scalar and LightGBM. That label, MaxAbs Scalar, is a scaling technique. Each feature is scaled by its maximum absolute value. And LightGBM is the classification algorithm used to train the model. For instance, you train a diabetes risk classifier and notice one model shows done for missing value imputation and appears as MaxAbs Scalar, LightGBM, and you instantly know AutoML both fixed gaps in the dataset and normalized the numeric features before training a strong tree-based classifier, making the pipeline easier to defend and reproduce. Now we see the moment where AutoML delivers clarity and confidence, finding the best run and understanding why it won. Because you defined a primary metric up front, AutoML makes it easy to identify the top performing model at a glance. From the Models tab in the Azure Machine Learning Studio, you can customize the view to surface additional metrics that matter to your scenario and go beyond scores by generating model explanations. This ensures you're not just selecting a model because it performed well, but because you understand its behavior and impact. For instance, after running AutoML for a diabetes risk classifier, you quickly identify the best run based on accuracy, then review explanations to confirm which feature influenced the predictions most. This visibility helps you move forward with confidence, whether your next step is deployment, stakeholder review, or further optimization. Now let's bring this to life with a quick demo. In this walkthrough, we're going to train a classification model using AutoML in Azure Machine Learning, the same approach teams use when they want strong baseline performance quickly without manually testing dozens of algorithms and configurations. You'll see how AutoML explores models, evaluates results, and surfaces the best candidate for your data and business objective. This is a powerful starting point for real-world ML projects, and it sets the foundation for everything that follows in our ML Ops lifecycle from optimization to deployment and monitoring. So for this demo, we're going to use AutoML, and we're going to go use that to determine the optimal algorithm and pre-processing steps to perform multiple training runs in parallel. And this is important because in real projects, you rarely know the best algorithm up front. AutoML is going to give us a structured way to explore the search space here. And instead of manually trying one model at a time, we're going to let AutoML do its magic for us. Now we have all the necessary resources here, and what we've done is we've opened up the train classification model with automated machine learning here. What we're going to do is we're going to take a look through it first, and in this example we can do a lot with this. So before we start, we're going to go in and look at these here, the cells, and we're going to take a little bit of a run. We're going to run this first cell here, and let's see what it does. We're going to run the cell and everything below it. And what you can see is before we start, we have to set up a few things to make it run. So we have that running, and we have to connect to our workspace. So when we come to our workspace, we have to get authenticated, and there's the option there. And then we go down here, and we have to give it some of our information about our environment. So we have that listed there. And then we also, we have just a few more things here to look at and set up. We need to get a handle for the workspace, and then we can go into preparing the data. And we're going to take a little bit to run this. The preparing of the data is one aspect of this. And I do want to mention here, when we talk about AutoML, which is what we're going to do with this script here, this notebook that's going to create some of a model for us is what we're doing. And we're going to go back behind the scenes, and we're going to make a pipeline in parallel. And it's going to try out different algorithms for us and parameters. And with each iteration, it'll produce a model with a score. And then the system will help to surface the best performing candidates based on the metric that we want to have optimized here. So it's not just training a single model. It's going in and it's doing an evaluation, and it's going to evaluate multiple candidate pipelines for us, and it's going to compare them with the metrics, and then it's going to really help us ultimately, once this finally runs all the way, it's going to help us to identify a strong baseline more quickly. And this is really important, especially in ML Ops, because you want a repeatable way to discover high-performing models. And we don't just want a process that depends on memory or manual trial and error. So the AutoML is a very good option. And as you can see right here, we are preparing the data. And so we're going to use this diabetes training table. As you can see here, it's setting it up. Then we want to configure the automated machine learning down here. And so it's going to create a compute cluster. And then you can see the name that it's going to work with here. It's also going to set the diabetic as the target column that we are trying to decipher. Well, also we have to set accuracy as the primary metric. It's timeout after 60 minutes of total running time, if not sooner. And notice too, it's going to train a maximum of 5 modules. And we're going to use that logistic regression algorithm, as you can see a little bit lower here. And we're configuring the classification job right here too. Some of the things we've mentioned, I'm going to set some limits on, and I'll show you in a little later demo how to do some of this another way through a notebook. You can actually do this through the GUI, so we'll get an option to see that a little bit later too. And we're going to set the training here, and you can see the logistic regression, and then we're having it run automated learning job for us here. And so you can see, and we're checking too to see each step that it processes correctly. And so here we're submitting the job, and then we're wanting it to be monitored also. Okay, so the monitor job is out there. So if I want to go in, I can click on this and I can monitor my job. This is one way to do it. So I could try clicking on this so that we can get that window, and we can sometimes, it takes a little bit for it to load here, but it should be able to give us a little bit more about what ran. And there it shows us the job. Now another way to get into this is we could just scroll down here and have found the jobs in that same area. Now you can see the job is running. You can see the data set. I'll scroll down a little bit here and you can see the cluster. It's running on the classification tab. I'll go in and view some of the configuration settings in there and see a little bit more about what it's noticing. And then we can go in and look a little bit more and see some of the settings we've adjusted here through our notebook. And then I can go down and you can see a little bit more, and we can get the information maybe in YAML or JSON if we wanted to see that. Now, we don't have a lot to look at here, but we're kind of going to let it cook for a little bit. But eventually, what we would see is we're going to start seeing models and models in child jobs. And I'll eventually show our data guardrails also. We'll eventually get a little output log, and there are some child logs there, so you see what's ready. And we can even notice there's currently a job running, so we could get a little deeper into that job and we could see extra information just about it if we wanted to do that. So we can see some of the options here. If I can get some metrics on that, maybe too, we can get a little deeper in. Maybe it's a little too early for that kind of thing here. We'll have to come back and look at it. I'm just going to walk my way back here and look at our initial job. And it looks like there might be a job called modest. And you can see here, it's a little bit more information being added. And it does take a while to kind of cook this. And again, it's really premature. So I'm going through some of the guardrails right there, as you can see. And the data guardrails, it's taking a look at there, and you can see it looking for class balancing detection. Missing feature values are also here, and we can learn more about each of these as we go through this class. While this is running, I do want to check out data for a moment, and I'm going to go click on data, and you can see it right here. This is what it's set up, it's where it set up the data store. So we have the data itself right here. Here's the training information right here. So I can go into that. And as I go into it, I may also want to scroll down a little bit and see a little bit more about the data store. So it gives you a lot of information. I can maybe browse it if I wanted to. You can get the data store and the storage there also if you need to. So we can see a little bit more information through here. So if I go in, let's see if I can get a little bit more information. Maybe it's available, maybe it's not. We'll have to see, but as we go in, okay, we can see it's just a blob where it's stored, and you can see some of the files that are used. So this is our data source. See if we can see the preview a bit here too. We might be able to, yeah. You can see a little preview of what that data looks like. You can create other data sets. I'm going to go back to this here. So this gives us a little browse where we can see, I can maybe see a little bit more here, what it's consumed. So I'm going to give it a little bit more, and you can see the code here, and you can see the job, and I might want to do a little bit more exploration. So here's another way to kind of get the data, get a preview of what information it's using to run the model here, to try to figure out, what are the ways to predict whether someone has the potential of being diabetic or not. And so this kind of classic example that we're using here. Now notice we have two jobs that are running. So one of them is complete. Let's take a look. Let's see what we can see. Do we have any metrics on this job? Nope. Yeah, I said some of this might take a little bit to run for us to get some information. So there's the main job right there. And then we may have some data guardrails from earlier. We saw that. We can see what passed, where it passed some information. And then the model and child jobs are out there. And this is the model right here. So you can see the accuracy there. And if I were to choose that model, let's see what we can get from it. We can get a few more things from it here. You can see the accuracy from here. We can go into metrics, and then we can look at the metrics, and you can see how accurate it was. And it's pretty accurate. It's pretty high, it has a pretty high rating, and you can take a look at some of the options there. And there's an accuracy table down below where it puts all the information together, and we have graphics for rock here, and you can see the calibration curve, and it's giving us a little bit of an idea of what's going on, not only just from the cards here, but you can also use these visuals, which are very helpful. And you can see now that there are a number of things that I have here that are in preview. So I don't think we have the responsible AI showing just yet because of the requirements. So these other ones, you may not be able to see. There's a little bit there. It's still processing though. But right here, you can see a little bit of the data source, the numeric, and you can also see a little bit more through the diagram that illustrates our data pre-processing and how it went through the process here. And so that could be helpful. And then we could also see the test results if it's here. Let me see. And okay, so yeah, it might take a little bit more for that to show up. And so that's the algorithm right there that we're using. And you can see its list, and you might be able to take a little bit of kind of a flush of all of that out into the output log. So notice there's a number of logs that are already created here. And there's the accuracy table. So you kind of can see the raw data there. Here's the confusion matrix. And so it's giving us a little bit, and there is the syntax there for running our AutoML. So it's going to come up in even more models, and it's really going to try to give us the best option that it can find. And we can see if, so there's a lot that we can take in here. And I'm going to go back into the jobs. Notice all of this experiment we've had. Here's the latest job right here. And if I click on the experiment, I get a little bit of a different experience in there. It shows me the job that we just saw. It's currently running. And then I go a little bit deeper here and eventually find more models. Okay, so it's finding a couple of models. It created a number of models, and it sorts it by which one has the highest rating. So from high to low, and it gives us the most accurate to the least accurate. So this could be helpful. It shows you what it found there. So this could be very helpful. And it looks like one of the other experiments completed here. So let me go out here and see if it's still running. It looks like it still might be. But if I go back to the jobs, there's that experiment. And I think it's telling us it did a lot of the pre-processing already. So like I said, it just takes a little bit of time to run this. And then we can see how many models are out there. And I created a number of models. There's 2 right there, and it's telling you that the algorithm that was used, and there's 2 more. So it's about 4 to 5 models that were created. So this could be very helpful, giving you the benefit of what all the models that it ran, and it's sorting them, which one's the most accurate. That could be very helpful. So we either have to decide what algorithms to use, or we can let it decide using AutoML, which could be very helpful. So let's see if we can get a little more information. So we see this AUC macro weighted lot. There's a micro one also. We can glean some information from that. And again, our table down below. So this is hopefully giving you a really good look at what's going on under the covers here. And what you will note is we do have a lot of options we can explore. And really what happens is that you have to dig a little bit further into these so that you can kind of see a little bit of what's there. And the metrics can be very helpful too. As you can see, the model actually is performing very, very well with a very strong class separation here and consistently high precision and recall. And we can see that this is important. If classes are imbalanced, we want to take a closer look. So what we're seeing with this demo here is a key takeaway is the speed with confidence that we get from this, because AutoML removes all the heavy lifting of choosing a model, having to process features, and also the hyperparameter tuning, which can take a lot of time. And there's a lot of guesswork maybe that's involved with that for most of us. And this gives us a way to validate models backed by very transparent metrics, as you can see. And then it gives us a way to easily go in and do some comparisons. Also, AutoML here can help us a lot. It's really fast from production to models. So moving data to production-ready models faster, and it still gives us full visibility to what was tried and what worked best and why we can trust the results. And it's also very handy. So I hope you enjoyed this presentation and hope to see you in the next. Now it's time for our knowledge check. Question 1. A data scientist wants to use automated machine learning to find the model with the best AUC weighted metric. What parameter of the classification function should be configured? Answer: primary metric. Question 2. A data scientist has pre-processed the training data and wants to use automated machine learning to quickly iterate through various algorithms. The data shouldn't be changed. What should be the featurization mode to train a model without letting automated machine learning make changes to the data? Answer: off. Now you've seen how ideas evolve into real working models by exploring data, choosing the right task, and using AutoML to experiment quickly while staying intentional and cost-aware. This section was all about building confidence through iteration, testing assumptions, understanding what AutoML does for you, and learning how to guide it toward meaningful outcomes. With a strong baseline model in hand and visibility into why it performs the way it does, you're ready to move beyond experimentation. Next, we'll shift from how well a model performs to how responsibly it performs, comparing results, interpreting metrics, and evaluating fairness, explainability, and trust using the responsible AI tools that bring machine learning into the real world. Thank you for joining us in this session. To continue your learning, watch other videos in this course or explore more on Microsoft Learn at aka.ms/learn.